Greetings and welcome to Lesson 8.3, Building Confidence Levels for Population Proportion.
Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue.
When dealing with population proportion, you should always think of binomial distribution. We're only given the amount of successes or failures, and we're going to be dealing with P's and Q's. Our point estimate this go round is going to be something called P prime. It's also notated as P hat with a little arrow up on top of it, but I'm going to stick with the book notation and go with P prime. So the confidence interval is going to be our point estimate minus our error. P prime minus our error bound proportion, so EBP instead of EBM, and P prime plus our error. So how do we get P prime? Well, P prime is just the number of successes, X over N, divided by N. So X divided by N. And how do we calculate our EBP? Very similar to what we were doing before, but this time we're going to go back to Z, get our Z-score, and then multiply that by the square root of P prime times Q prime all over N. Now remember, if Q was 1 minus P, then Q prime must be 1 minus P prime. Let's do a thorough walkthrough. Suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adults, residents in the city, are surveyed to determine whether they have cell phone. Of the 500 people surveyed, 421 responded yes, they own cell phones. Using a 95% confidence level, let's compute the confidence interval estimate for the true proportion of all adult residents of the city who have a cell phone. These 5 steps are exactly the same 5 steps, pretty much, as we've been doing, except one small thing. Instead of figuring out or calculating our X bar, we're going to calculate P prime and Q prime. And then we're going to find a Z-score that goes along with our confidence level. Because it's a Z-score, we can refer back to the table if it is one of the common confidence levels. Third step is we're going to calculate our error. So what that it's called an EBP, so this time instead of an EBM. We don't care. We're just going to calculate that error. Fourth step, we're going to put together our confidence intervals by P prime minus our error, P prime plus our error. And then final step, as always, we're going to interpret the results. So pretty much the same 5 steps, a few little different calculations, but overall, it's the same process. So let's do step 1, calculate P prime and Q prime. P prime is going to be the successes over our total number. Our successes are 421 divided by the number of people surveyed, which is 500. 421 divided by 500 is 0.842. Let's calculate Q prime. Q prime is 1 minus P prime. So 1 minus our 0.842 is 0.158. Step 1 done. We have figured out P prime. We have figured out Q prime. Step 2. Let's find our Z-score for our confidence level. Our confidence level is 95%. That is a completely common confidence level. So I go and look at my little table and I find the corresponding Z-score of 1.96. Step 2 done. Step 3. Let's calculate the error. The error is Z times the square root of P prime times Q prime, all divided by N. We have that information now, so let's start plugging in our values. P prime is 0.842. Q prime is 0.158, and N was 500. Z is 1.96. So 1.96 times the square root of 0.842 times 0.158, all divided by 500. Throw that into a calculator and we get 0.032. Third step completed. We have our error. Fourth step, let's calculate our confidence interval. P prime minus our error and P prime plus our error. P prime minus our error would be 0.842 minus 0.032, giving us 0.810. And P prime plus our error is 0.842 plus 0.032, and we get 0.874. Our confidence interval for our true binomial population will be the 0.810 to 0.874. So let's interpret the results. We estimate with a 95% confidence that between 81 and 87.4% of all adults in this city have cell phones. Granted, we changed our decimals over to percentages, and they actually make more sense when we're talking to somebody to say the percentages versus the decimals. It would be okay to say decimals, but if we were actually talking to somebody, you would want to say, hey, we're 95% confident that between 81 and 87.4% of all adults in the adult residents in the city have cell phones. It's just a way of communicating the results verbally versus having it down on paper. There is a certain amount of error introduced into the process of calculating confidence intervals for a proportion. Because we don't know the true proportion, we're forced to use these point estimates, and they're okay, but data has shown, studies have shown that this method is really kind of flawed. Because of that, there is a simple adjustment. It's called the +4 adjustment. And all that means is we're going to do two adjustments. The first thing, we're going to add 2 to the successes, 2 to the failures, and 4 to the sample size. So our X value will be bumped up by 2. Our N will be bumped up by 4. Because we don't really care about the numerical amount of failures, because we're going to calculate our P prime using our X, we don't need like a Y to say, oh, and the no's were 10 plus 2. You don't need to do that. Just concentrate on adding 2 to the X's and adding 4 to the N's. Why 4? Because you added 2 to the yeses and 2 to the no's, and that seems to balance everything out, this adjustment, believe it or not. So let's take an example and see it in action. A random sample of 25 statistics students was asked, have you smoked cigarettes in the past week? 6 students reported smoking within the past week. Use the +4 method to find a 95% confidence interval for the true proportion of the statistics of students who smoke. The only difference here between the previous example is we're going to do that adjustment up front first. So our success, our X, is 6 students. So I'm going to take X and add 2 to it. So 6 plus 2 is 8. Our N was the sample of 25 statistic students, and therefore I'm going to take my N and add 4 to it. 25 plus 4 is 29. So working with the 8 and 29 from here on out, we're going to complete this problem. First step, next step, is calculate P prime and Q prime. P prime is the successes over the number of sample size. So 8 divided by 29 is 0.2759. Q prime is 1 minus p prime. So 1 minus 8 over 29 is 0.7241. Now you could use, instead of the 8 over 29, you could use the 0.2759 for your calculation. And I really did, but I wanted to show you that I am using the true p prime of the 8 over 29 and not 6 over 25. Now we need to calculate our error. Our error is calculated as our z-score times the square root of p prime times q prime all over n. The z is one of the common confidence intervals at 95%, so 1.96. So let's throw all these values in. 1.96 times the square root of 0.2759 times 0.7241, all divided by 29, and that equals 0.1627. That's our error. Next step, calculate the confidence intervals. Take your p prime minus the error, p prime plus the error. When you do this, you get 0.759 minus the 0.1627, getting 0.1132. And adding those two together, you get 0.4385. Last step, let's interpret it. We are 95% confident that the true proportion of all statistic students who smoke cigarettes is, since I'm saying verbally, 11.3% and 43.9%. So if I was saying it verbally, I would probably change it over to percents. If I'm just writing it down on paper, I'll go ahead and leave it as decimals. Now, I do want to say I did calculate this problem without the adjustment. And the interpretation would be, we are 95% confident that the true proportion of all statistics students who smoke cigarettes is between 7% and 41%. So you can see there is a difference between the 11% and 7%, and let's call it 44% and 41%. There is an adjustment that we did. And it's not saying that our original, if we didn't do this +4 adjustment, would have been incorrect. It's just this adjustment has shown that for these small values using these proportions, it's just a better guess. It's a better calculation. I don't want to quite say guess, but it is a better calculation for the true proportion. I want to run through building a confidence interval for a proportion two different ways. First, I'm going to use the pre-programmed function in the TI-84 Plus to show you how to do it very quickly. The second way I'm going to show you is, well, I'm going to have to do this kind of manually for those of you that don't have the TI-84, because it's very important where you get your parentheses. So I want to show you the long way and the short way. So first of all, let me talk about the problem we're going to work with. The Berkman Center for Internet and Society at Harvard recently conducted a study analyzing the privacy management habits of teens internet users. In a group of 50 teens, 13 reported having more than 500 friends on Facebook. Use the +4 method to find a 90% confidence interval for the true proportion of teens who would report having more than 500 Facebook friends. I'm going to run through the long way first. That way you can really appreciate the power of the TI-84 Plus. Because I'm using the +4 method, I am going to adjust things slightly. First of all, my X value is 13. I need to bump this up by 2 using the +4 method. My N value is 50. Bump this up by 4. My X value I will be using is 15. My N value I will be using is 54. Now I want to calculate P prime and Q prime. P prime is the 15 divided by 54. And Q prime is 1 minus this. So 1 minus the previous result of 0.2778. So our P prime is 0.2778 and our Q prime is 0.7222. Now what is our Z? If we want to build a 90% confidence interval, I'm going to use 1.645 as my Z score. I have my Z. It's a common one, so it's one of those things that you just kind of memorize over time. I have my P prime. I have my Q prime. Now I'm ready to calculate my error. My error is going to be my Z, 1.645 times the square root of, now my numerator is going to go all into a parenthesis. My P prime is 0.2778 times my Q prime of 0.7222, that is all my numerator, divided by my N of 54. That is all inside the square root. Now, this calculator, I have to get out of the square root by hitting the arrow. If you do not have a calculator that does that, then you're going to have to add a few more parentheses. One in the very front. So I would have to go right in the front and I would have to enter a parenthesis, so I'd have these double parentheses, and one at the very end to be able to do this calculation correctly. So it's very important where you have your parentheses. Have a parenthesis around the whole entire thing that's inside your square root. Have a parenthesis around your numerator, and you could even have parentheses around your denominator. There's no harm, no foul there. And I get my error of 0.1003. Now that I know my error, I'm going to find my low end of my confidence interval and my high end of my confidence interval by taking my P prime and subtracting out my error, and then taking my P prime and adding my error. So 0.2778 minus my 0.1003. My low bound is going to be 0.1775. Taking my 0.2778 plus the 0.1003. The high bound is 0.3781. So my confidence interval would look like this. All right. So my low bound versus my high bound. And I would still have to interpret this. So I would say we are 90% confident that between 17.8 and 37.8% of all teens would have reported having more than 500 Facebook friends. Now let me show you how to do this programmatically. I know what my X value is adjusted. That was 15. I know my N value adjusted is 54. So I'm going to go to Stat. I'm going to go to tests, and there are a whole bunch of tests. Be careful not to choose any of these, either 5 or 6, proportion Z test or proportion Z test. So if I go into one of these, you're going to see this is not the area you want. So just get out of there. Go back into Stat. I just wanted to show you because I've done this in the past and I get too anxious and I grab the wrong test. So really where it is if you click up, we want this A test, proportion Z int. Proportion Z int. So one value of X, proportion Z. So I'm going to go down to A. I could also type in A by using my alpha A. That might be faster. And go enter. Now it wants my X value, 15, my N value of 54, and make sure you have your right confidence interval of 0.90, and hit calculate. That's it. Yes, it is very quick. It is very easy. When you're using the TI-84 Plus, it does all the background math for you. I do want to have you look at one thing. See this little icon right here, the P with this little arrow? That is called P hat. A lot of things that you look up on the internet will use P hat. Our book uses P prime, so I'm going to stick with P prime. Otherwise, that's it. That's how you calculate the confidence interval for a proportion. Use the proportion zint function under stats and tests. Until next time, be seeing you. Occasionally, we want a specific margin of error, and therefore we can use the error-bound formula to calculate the required sample size. To do that, I'm going to take the error-bound formula and I'm going to solve for n, because that's really what my unknown is. And once I manipulate the error formula, I get n equals rz squared times p prime times q prime all over our error squared. We have this information. With some slight calculations, we can plug in all these values and solve for the n that we need. So let's take a look at an example. Suppose a mobile phone company wants to determine the current percentage of customers aged 50 plus who use text messaging on their cell phones. How many customers aged 50 and above should the company survey in order to be 90% confident that their estimated sample proportion is within 3 percentage points of the true population proportion? Now, we have the formulas we're going to use. Looking at our n formula, we're going to need a z, we're going to need our p prime, our q prime, and our error. We are given our error. We want to be within 3 percentage points of the true population proportion. So that's going to be 0.03. 3 percentage points, transfer that over, so 3% transferred over to a decimal is 0.03. Our z is based on our confidence level, and 90% is one of those common, so 90 relates to a z of 1.645. Now, we do not have our p prime or q prime. And because of that, we're going to use the biggest p prime we can use and the biggest q prime that we can use. We're going to be conservative. And to do that, our largest p prime that we can have is 0.5. Why? Because p prime plus q prime is 1. And the largest p prime can be 0.5 and the largest q prime can be 0.5, because 0.5 plus 0.5 is 1. Now, if I selected any other p prime, as in 0.7, then the q prime would not have been maxed out. That would have been at 0.3. And of course, 0.5 is larger than 0.3. So the largest p prime and q prime combination would be this 0.5. So I'm going to use 0.5 for my p prime. I'm going to use 0.5 for my q prime. I'm going to throw this all into the equation. Rz squared, 1.645 squared, times 0.5 times 0.5 all over 0.3 squared. Working out that calculation, we get 751.67. Now, how many people should we survey? We can't ask a 0.67 of a person, so let's always round up. So the sample size should be 752 in order to be 90% confidence within the 3 percentage points of the true population proportion. So all of that goes together.
You've reached the end of this lesson.